Welcome to our presentation of the Frese FUELSAVE concept, Intelligent Engine Room Flow Management for Cooling Water Systems. Frese FUELSAVE ensures the optimal balance of your cooling water systems. It continuously prevents inefficiencies and secures consistent performance, even under varying operating conditions. By optimizing energy usage and minimizing waste, the system maximizes fuel efficiency while reducing overall energy consumption. This translates directly into significant cost savings. Frese FUELSAVE is not only effective but also a smart investment. Return on investment is typically achieved within 1 to 3 years, thanks to total fuel savings of up to 10%, with most vessels achieving between 3 to 6%. In today's maritime industry, compliance is key. Frese FUELSAVE helps your vessel meet environmental standards by improving EEXI, EEDI, and CII ratings, ensuring sustainable operations and regulatory confidence. The proven and patented Frese FUELSAVE system provides tangible benefits for your fleet. Optimized system balance, reduced fuel and energy costs, fast return on investment, full alignment with environmental compliance standards. To learn more, simply scan the QR code and explore how Frese FUELSAVE can transform your vessel's efficiency. Frese AS is a Danish company with a proud history, founded in 1944. Our headquarters is located in Slagelse, just 100 kilometers west of Copenhagen. In 1988, Frese introduced its first dynamic valve, the Frese S1, a milestone that positioned us as a pioneer in the industry. Since then, we have supplied approximately 10 million dynamic valves worldwide, establishing a strong global presence. At the end of 2024, Frese joined forces with PICV Group, a leading Finnish valve manufacturer, marking a new chapter in our journey of innovation. Today, as part of the PICV Group, Frese continues to deliver innovative valve solutions with a focus on energy efficiency, reliability, and sustainability. Our heritage and expertise, combined with PICV's global reach, ensure that Frese AS remains a trusted partner for dynamic flow solutions worldwide. Frese is structured into dedicated business units, each designed to focus on the unique challenges of our customers and industries. First, the Marine Business Unit, where we deliver advanced flow management solutions that improve fuel efficiency, reduce emissions, and ensure compliance with international environmental standards. Next, the HVAC Business Unit, which provides energy-efficient valve technologies for heating, ventilation, and air conditioning systems, ensuring comfort, reliability, and significant energy savings in commercial and residential buildings. Our District Energy Business Unit supports large-scale heating and cooling networks, helping cities and communities achieve sustainable and resilient energy distribution. Finally, the Industrial Business Unit, where we deliver customized solutions for specialized applications, meeting the high demands of process industries with innovative and reliable technologies. When we look at a vessel's typical operational profile, we notice a significant difference between design conditions shown to the left and the actual operation, where a typical example is shown to the right. The main engine is rarely used at its full design load, and auxiliary engines often run under varying conditions. In the example shown, we see that the main engine typically runs at a load between 35% and 50% of its full capacity. The auxiliary engines most of the time run at a load between 25% and 50%. This gap between design and reality creates inefficiencies, especially in cooling systems where unnecessary energy is consumed. So, how can so much energy be saved? The key lies in achieving an optimal balance in cooling water systems while simultaneously eliminating the risk of starving critical units that must have the design load available at all times. By regulating flow and preventing overpumping, Frese solutions eliminate wasted energy, reduce fuel consumption, and create a more efficient operation of the entire vessel. This optimization leads to measurable savings in both energy and cost, while also supporting environmental compliance. In real-world operations, vessels typically require only 25 to 50% of the design cooling water flow. According to the pump affinity law for centrifugal pumps, the pump energy is calculated by the cube compared to the system flow. This means that when the flow is reduced to 50%, the pumping energy required drops dramatically, down to just 12.5%. This reveals a significant opportunity. By actively controlling flows, owners and operators can cut unnecessary pumping energy, reduce fuel consumption, and improve overall system efficiency. So, how can so much energy really be saved in cooling and heating systems on a ship? The answer lies in maintaining the optimal flow balance in cooling water systems, thus ensuring that only the cooling water required is guided towards each consumer at all times. By aligning system performance with actual operating conditions, Frese FUELSAVE unlocks both energy savings and operational reliability, ensuring efficiency without compromises. Frese offers a complete portfolio of innovative valves, each designed to optimize flow control and energy efficiency across applications. All valves work by the same mechanical principles that eliminate pressure fluctuations across the valve opening. The Alpha Flow Limiting Dynamic Valve provides a fixed cartridge design for a predetermined maximum flow. Simple, reliable, and effective. The cartridge is positioned in line, and the flow setting cannot be tampered with. The Sigma Compact Flow Limiting Dynamic Valve goes a step further, offering manual adjustment of the flow by a handle that will adjust the opening of the valve, thus allowing flexibility to fine-tune the system after the installation process. The Optima Compact Pressure Independent Control Valve is equipped with an automatic actuator that constantly adjusts the flow to all flows between design load and zero. This ensures optimal control, stability, and efficiency, even under varying system conditions. Finally, the Omega Compact three-way temperature control valve reduces pump energy by providing the lowest pressure drop in its class. The leakage class of the Omega is Class 4, meaning that the maximum leakage is 0.01% of the design flow. It combines low leakage rates with easy maintenance and a compact design, making it the smart choice for demanding applications. A PICV, or Pressure Independent Control Valve, is a smart solution for modern hydronic systems. It combines three functions into a single valve. It works as a control valve, regulating flow precisely at all part loads between fully open and fully closed. It has an integrated differential pressure regulator, ensuring stable operation even under fluctuating pressure conditions. It works as a flow limiter, preventing overflow and ensures that inefficiencies are always avoided. By integrating these functions, PICVs deliver constant and accurate flow control, regardless of pressure fluctuations in the system. This ensures optimal comfort, energy efficiency, and simplified system design. Furthermore, unlike all other PICVs in the market, the Optima Compact is designed in a way so that the motion of the actuated piston is unaffected by the presetting of the valve opening, since the direction of the piston is vertical while the presetting is set in a horizontal movement by means of two separate parts. For more details on the Optima Compact PICV, you can explore further at Frese's website. This slide illustrates the relationship between pump capacity and energy consumption in a vessel's cooling water system. The system is balanced by static valves. At full design load, the freshwater pumps each operate at 100 cubic meters per hour, alongside the main engine at 100 cubic meters, two gene sets at 30 cubic meters each, and additional consumers with smaller demands, 20, 10, and 10 cubic meters respectively. Altogether, this results in a total pump capacity requirement of 200 cubic meters per hour at 100% load. At design load, the pump energy consumption is also 100%. Again, the same system, but in this scenario, the main engine is off, while one generator operates at full load, consuming 30 cubic meters per hour. The second generator is off, and the auxiliary consumers are running with varying demands. Consumer X at 20 cubic meters, Consumer Y at 50% of its design load, and Consumer Z at 10 cubic meters. The two freshwater pumps are still rated for 100 cubic meters per hour each, leaving a total pump capacity of 200 cubic meters per hour. However, when we examine pump energy consumption with static valves in part load condition, a critical issue becomes clear. Even though the actual demand is far below the design capacity, the pumps continue to consume disproportionately high energy, 100%. The reason behind this is that if we attempt to lower pump speed to save energy, consumers still operating at design load risk being starved of flow. This illustrates the inefficiency of static valve systems under part load conditions and emphasizes the need for smarter, dynamic flow control to align pump operation with real demand. In this example, we return to full design load conditions. Two freshwater pumps rated at 100 cubic meters per hour each, supporting the main engine at 100 cubic meters. Two generator engines at 30 cubic meters each, and additional consumers at 20, 10, and 10 cubic meters. This totals a pump capacity of 200 cubic meters per hour. But unlike static systems, here we apply dynamic valves. Dynamic valves automatically regulate flow, ensuring that each consumer receives exactly what is needed. No more, no less. The dynamic valves offer advantages such as flexibility. One pipe loop can be closed without influencing other parts of the system. Also, the commissioning process is simplified. However, when the system runs at full capacity, the pumps are running at an energy consumption also at 100%. In this operating scenario, the main engine is offline and only one generator is running at full load, consuming 30 cubic meters per hour. The second generator remains off, while Consumer X operates at 20 cubic meters, Consumer Y at 50% of its design load, and Consumer Z at 10 cubic meters. Together, this results in a total demand of just 65 cubic meters per hour. With dynamic valves, the pumps can freely, by means of a variable frequency drive, be adjusted to match this reduced flow. Unlike static systems, where reducing pump speed risks starving consumers, dynamic valves ensure that all units, even those running at design load, continue to receive the correct amount of cooling water. As a result, pump energy consumption drops dramatically, in the shown scenario down to just 7%. This example highlights how dynamic valve technology enables safe reduction of pump speed without risking starvation of critical consumers. Thereby, significant energy savings are unlocked with improved efficiency and lower operating cost as a result. This slide is a compilation of the 4 previous slides in one matrix. Above the green dotted line, we see the engine room fitted with static balancing valves. To the left at design load and to the right at part load. Below, we see the same system, but now equipped with pressure-independent valve technology. Again, to the left at design load and to the right at part load. Only in the scenario to the bottom right, pressure-independent valves at part load, it is possible to harvest the potential savings that are given by the operational profile of the vessel. This without compromising safety on board. The critical consumers will always have their design cooling capacity available if need be. The Frese FUELSAVE consists of 6 elements in total: seawater on the primary side of the main exchanger, low-temperature freshwater cooling on the secondary side, engine room fan speed control, main engine high-temperature freshwater cooling, and the dump condenser. Each part is valuable on its own, but together they deliver unmatched performance. At the heart of this integration lies automation. It ensures seamless communication between all components, reducing human error, optimizing processes, and unlocking real-time adaptability. In summary, combining these technologies creates a system that is not just efficient, but smarter, greener, and more cost-effective. The Frese FUELSAVE solution is designed to optimize both seawater and low-temperature freshwater cooling systems. Its primary goal is to ensure efficiency, reliability, and fuel savings. The system consists of 3 steps. 1. Introduction of variable frequency drive for the seawater pumps. 2. Introduction of variable frequency drives for the low-temperature freshwater pumps. This part introduces some challenges that need to be addressed by letting the pumps fluctuate in pressure without managing the flow for the individual consumers. We introduce a risk of starvation of individual consumers, overflow in parts of the system that causes a low delta T. 3. To overcome these risks, we introduce individual flow control of each cooling water, consumer securing optimal cooling of all consumers. The valve package consists of Omega 3-way temperature control valve, Optima compact pressure independent control valves, Alpha and Sigma compact pressure independent balancing valves. The overall automation package is guided by a differential pressure transmitter placed in the loop of the system that meets the highest resistance, the so-called index loop. By combining these technologies, the FuelSave system improves operational stability, reduces pump energy, and minimizes overall fuel consumption. This results in lower emissions, reduced operating costs, and extended equipment lifespan. In summary, the Frese FuelSave system is a robust and sustainable approach to marine cooling water management. The Frese FuelSave system integrates advanced control algorithms with continuous monitoring of cooling water circuits. Sensors track key operational parameters such as flow rate, differential pressure, and temperature. These inputs feed into the FuelSave controller, which calculates the optimal balance point in real time. Based on this data, the system adjusts pump speed through variable frequency drives and regulates dynamic control valves to match actual demand. This prevents overpumping and ensures that each consumer, whether the main engine, auxiliary engines, or secondary loads, receives the correct amount of cooling water. The system's signal architecture provides operators with continuous feedback. Analog signals communicate flow and pressure conditions. Digital outputs deliver alarm statuses and control confirmations. An integrated interface connects directly to the vessel's automation and monitoring systems. This closed-loop design guarantees that performance remains stable under all operating conditions, while minimizing pump energy consumption and securing maximum fuel savings. In practice, the Frese FuelSave transforms flow control from a static setup into a fully automated, responsive system, delivering both operational reliability and measurable efficiency gains. Within the Frese FuelSave system, the engine room ventilation fans are integrated into the same advanced control logic as the pumps and valves. Each fan is equipped with a variable frequency drive, which allows the system to continuously adjust fan speed according to real-time operational data. Fans may also be operated in a cascade mode. 2 primary control inputs are used. Engine room air temperature, monitored through strategically placed temperature sensors, and the main engine load index reflects the vessel's current power demand. When the load index is high or engine room temperature approaches the set point, the fans are driven toward higher speeds to ensure sufficient airflow and maintain a safe working environment. Conversely, if the measured temperature falls below the predefined set points, the system reduces fan speed, decreasing airflow while still maintaining the minimum static pressure required in the engine room. The control loop ensures that ventilation demand is precisely matched to actual thermal load, avoiding the inefficiency of running fans at full capacity under all conditions. From a signal perspective, the system provides analog feedback of fan speed and power consumption, digital alarms for deviations or drive faults, and full integration with the vessel's automation and monitoring system, allowing operators to track performance in real time. By applying this closed-loop control strategy, FuelSave not only reduces fan energy consumption, but also minimizes noise, extends equipment lifetime, and contributes to the overall fuel-saving potential of the vessel. Boiler optimization within the Frese FUELSAVE system is achieved through a combination of precision valve technology and intelligent control strategies. The first key element is the low-leakage three-way valve, installed on consumers requiring preheating while the vessel is in port. For example, the main engine high-temperature three-way valve ensures stable flow and temperature control during preheating cycles. The second component is the atmospheric dump condenser, combined with an LTFW control valve, either two-way or three-way, depending on the design of the low-temperature freshwater circuit. This arrangement allows precise control of steam condensate temperature, improving boiler efficiency and protecting downstream equipment. For these applications, Frese offers the Optima Compact and Omega Compact valves. The Optima Compact PICV provides automatic pressure-independent flow control with actuator integration, ensuring consistent thermal balance. The Omega Compact offers a robust three-way design with low leakage, compact footprint, and easy maintenance, ideal for dynamic boiler applications. Additionally, an optional standalone control and sensor package can be supplied for both valve types. This package includes dedicated sensors and controllers that integrate directly with the ship's automation system, delivering real-time monitoring, temperature feedback, and fail-safe control. Altogether, these components ensure that the boiler system operates at maximum efficiency, with minimized thermal losses, optimized preheating, and improved reliability of auxiliary equipment. This diagram demonstrates the impact of valve leakage on boiler performance. When the steam preheater is operating, the three-way valve should be fully closed toward the low-temperature freshwater supply. If the valve is leaking, however, cooling water continues to enter the loop. This means that instead of remaining at its set point of around 85 degrees Celsius, the water is unnecessarily cooled down. This temperature drop forces the steam preheater to inject more steam to achieve the desired outlet temperature. The direct consequence is increased steam demand, which leads to higher fuel consumption in the oil-fired boiler. This scenario typically arises when the vessel is in port or during main engine low-load operation, conditions where preheating demand is highest. By applying low-leakage three-way valves as part of the Frese FUELSAVE system, this unnecessary cooling is eliminated. The system maintains stable water temperatures, minimizes steam usage, and significantly reduces boiler fuel consumption, improving both efficiency and operating costs. The atmospheric dump condenser is a critical component in boiler optimization, utilizing the low-temperature cooling water for condensing steam to be used in the HT circuit and oil-fired boiler. If the dump condenser is installed in parallel with other cooling water consumers, a two-way control valve is sufficient. This valve regulates flow through the condenser while allowing bypass flow directly to the other consumers. On the other hand, if the dump condenser is installed in series with other cooling consumers, a three-way valve is required. In this configuration, the valve diverts flow either through the condenser or bypasses it, depending on system demand and temperature conditions. For these applications, Frese offers both the Optima Compact and the Omega Compact valve solutions. By selecting the appropriate valve configuration, two-way or three-way, depending on the condenser's placement in the LTFW cooling system, the Frese FUELSAVE system ensures precise control of steam condensate temperature, minimizing fuel consumption and improving overall boiler efficiency. In boiler optimization, the condensate returns loop plays a critical role in fuel efficiency. If valve A is normally open and valve B is normally closed, the LT cooling water is led through the condenser. However, this configuration can result in subcooled condensate, meaning the condensate is cooled more than necessary before returning to the boiler. This excess cooling increases the demand for reheating, leading to unnecessary energy consumption. The impact of this optimization is significant. Avoiding subcooling reduces boiler fuel consumption by approximately 10%, which typically translates into an annual saving of around 14.5 metric tons of fuel for the vessel in the case example showcased. To achieve this, the Frese FUELSAVE system integrates the atmospheric dump condenser with either a two-way or three-way valve, depending on the existing LTFW design. This precise control of condensate temperature not only improves fuel efficiency, but also enhances the overall thermal balance and reliability of the boiler system. The savings potential of the Frese FUELSAVE system depends on several key operational factors. First, vessels that operate for extended periods at low main engine load or with auxiliary engines running at partial capacity will see the largest benefit. This is because pump systems are often oversized for real-world operating conditions, and fuel-save optimization aligns energy use with actual demand. Second, vessels spending many hours in port or at anchorage gain additional savings. During these periods, cooling water demand is lower, yet conventional systems still consume significant pump energy. FuelSave reduces this wasted energy. Third, the size of the installed pumps plays a direct role. Larger pumps offer a larger margin for optimization, which translates into greater absolute fuel savings. Finally, operations with varying cooling loads benefit strongly from FuelSave's adaptive control, which dynamically balances flows and prevents overpumping under fluctuating conditions. Taken together, these factors define the estimated fuel saving range per installed pump power. Typical savings fall within several percentage points of fuel consumption per year, representing a significant reduction in both operational costs and environmental footprint. In the shown calculation, the overall savings are between $95,000 and $134,000, assuming that the fuel price is around $650 per metric ton. The Frese FUELSAVE system delivers not only measurable fuel savings, but also ensures compliance with tightening environmental regulations. Based on independent data from Clarksons, and assuming a fuel price of €550 per metric ton, the typical return on investment for FuelSave ranges between 1 and 3 years. This calculation includes the costs of engineering, hardware, automation, and commissioning, though it excludes installation, which may vary by vessel. Beyond financial savings, the system supports compliance with international standards such as EEXI, EEDI, and CII ratings. By reducing fuel consumption, ships directly lower their CO2 emissions, ensuring they remain within compliance limits and avoid costly penalties. The result is a dual benefit: a rapid and reliable ROI for ship owners, and a strong contribution toward meeting sustainability and regulatory requirements. All figures presented are from installed and running systems. This is the DFDS case study with the vessel Lunar Seaways. After 12 months of operation, by January 2025, the Frese FUELSAVE system has delivered proven results in efficiency and savings, confirming its impact in real-world conditions. In the DFDS case study, Frese FUELSAVE was implemented with a clear scope of supply. The project included low-temperature freshwater optimization, boiler optimization, and full automation integration. By combining these elements, the FuelSave system ensures that the vessel's cooling and heating systems operate at maximum efficiency, while automation provides transparency and control for the crew. This comprehensive approach demonstrates how FuelSave delivers both technical performance and measurable operational savings on DFDS vessels. In this DFDS case study, Savings were measured on the low-temperature freshwater system under real operating conditions compared against the vessel's specified continuous maximum rating, or SMCR. While the system is designed for 100% SMCR, actual operations showed that the vessel typically runs at only 40 to 60% of SMCR. Under these part load conditions, static valve control forced the pumps to continue operating at design capacity, resulting in substantial overpumping and wasted energy. With Frese FUELSAVE optimization, the pumps were allowed to follow real demand. Flow was reduced in proportion to the cooling load, cutting pump energy consumption by up to 81% in harbour mode and 73.5% in seagoing mode compared to the static baseline in yellow colour. These verified results confirm that aligning pump operation with actual SMCR-based load conditions delivers both fuel efficiency and compliance benefits, while maintaining full cooling reliability across all consumers. This slide shows the verified before and after results from the DFDS case. Over the course of 1 year, optimization of the two low-temperature freshwater systems, forward and aft, delivered 432 megawatt-hours of energy savings. That equals approximately 100 metric tons of fuel saved, calculated using a specific fuel oil consumption of 230 grams per kilowatt-hour. In addition, boiler optimization generated a further 97 metric tons of fuel savings. This figure is based on DFDS's own boiler consumption study, assuming 0.25 tonnes per port stay across 388 port calls in 2024. Together, these measures provided a total saving of 197 metric tonnes of fuel. At a price of around $500 per tonne of heavy fuel oil, this equals nearly $98,500 in cost savings per year. With a total turnkey investment of $250,000, the result is a return on investment of just 2.5 years, confirming both the technical efficiency and the financial viability of the Frese FUELSAVE solution. The DFDS case demonstrates the full impact of the Frese FUELSAVE system. By optimizing both the low-temperature freshwater systems and the boiler operations, the vessel achieved significant verified fuel savings. The results confirm the system's ability to reduce energy consumption, fuel costs, and CO2 emissions, while also delivering a reliable return on investment. This case study highlights how FuelSave not only improves operational efficiency, but also supports environmental compliance, making it a proven solution for modern shipping. Here are a selection of partners and operators who have by now decided to introduce the Frese FUELSAVE system to their fleet. The types of vessels and the operational patterns of the vessels are very different, but all benefit from the system. This slide shows the already installed base of Frese FUELSAVE systems split into vessel types and divided into retrofit projects and new build projects. This slide shows the 5 steps that form part of a full Frese FUELSAVE project. The following slides will go into further details covering each step. In step 1, we begin with the Request for Information, or RFI. This is filled in by the customer and provides the essential data needed to evaluate the project. The RFI includes general vessel information such as IMO numbers, the number of vessels, and their operational profiles. It also requires details like specific fuel oil consumption for auxiliary engines, annual fuel consumption, and information on the cooling water systems, including seawater, low-temperature freshwater, and main engine high-temperature systems. Supporting documents are also requested, such as P&IDs, heat balance data sheets for cooling and jacket water pumps, boiler P&IDs, and records of annual boiler consumption. Additionally, information on engine room fans, nameplate pictures for all electrical motors, and ventilation drawings covering fans and ducts are needed. By gathering this comprehensive information, we ensure that the Frese FuelSave system can be designed and tailored precisely to the vessel's requirements, laying the foundation for a successful project. Step 2 of the project is the Frese FuelSave business case, prepared by Frese. In this stage, we present a complete commercial offer, including pricing and a clear return on investment calculation. Alongside the financials, a technical delivery report is provided, detailing the scope of supply and system descriptions. A dedicated fuel saving report is also included, supported by detailed calculations and diagrams. Updated P&IDs illustrate the placement of equipment, while electrical and wiring diagrams show how the system integrates with the vessel. As an option, an installation quote may be supplied through approved partners. The business case brings together commercial, technical, and operational insights, giving ship owners a full understanding of the benefits, costs, and savings potential of the FuelSave system. Step 3 is the onboard survey, carried out by Frese. This important stage verifies the design and ensures that the proposed solution is suitable for the specific vessel. During the survey, recommendations are made for the exact placement of equipment, considering space, safety, and accessibility. Additionally, cable measurements are performed to prepare for installation, ensuring accuracy and minimizing risks of delays or adjustments later in the process. The onboard survey provides the final confirmation that the system design is aligned with the vessel's configuration, creating a solid foundation for the installation phase. Step 4 is installation, which can be carried out either by the customer or by Frese. The mechanical installation includes fitting 2- and 3-way valves, brackets for variable frequency drives, cabinets, sensors, sensor pockets, and cable trays. On the electrical side, the process involves cable pulling, installation of VFDs, and retrofitting of existing motor starters. Automation is also integrated with a PLC, a control screen or panel, and the necessary software. In addition, a remote access module is installed to allow secure monitoring and support. This stage brings together all mechanical and electrical elements, ensuring that the FuelSave system is fully and reliably integrated into the vessel's operations. Step 5 is commissioning, conducted by Frese. This phase begins with the startup of the automation system, followed by thorough function tests on all valves, sensors, and safety features. Flow verification is carried out across every valve to ensure proper operation. Next, minimum differential pressure set points are determined and fine-tuned, along with the control and P&ID parameters for each control valve. Finally, a full performance test is conducted. This documents the energy savings achieved with the system running in automatic mode. The commissioning stage confirms that the FuelSave system is fully optimized, safe, and ready to deliver measurable efficiency improvements. Thank you for taking your time to learn more about the Frese FuelSave system and how you can obtain substantial savings for the operation of your vessels. Interested? Reach out and let Frese calculate a unique business case for a vessel of your choice.